Anyone?
Okay, so welcome everybody to our seminar today. So we have Thomas Louf with us, which all of you know. He's now finishing his PhD thesis. To me, let's say I'm happy for that, but it's also a pity because and yeah, because I mean he did such a great work. I mean he's really brilliant. He's very fast. He's one of those people who don't talk very much, but he prefers to speak with actions, let's say. So yeah, I mean, we had meetings with Jose. Jose is his supervisor, and then Jose and I started to let's say vague words about implementing a model who could explain the data, and he didn't say anything. And then in a week, he presented us the model, the simulations, the discussions, and almost a paper. And also he had very nice writing skills. So yeah, I mean, I wish I could hire him another 4 years, but I don't know if you like this. Anyway, yeah. So so hopefully will you present this fall your
the latest, yeah,
PhD work. Yeah. Okay. So this is like yeah, preliminary, let's say, presentation of his work. Okay. So the floor is yours.
All right, well, thanks a lot for the introduction. So yeah, this seminar, I'd like to talk about a couple of works that I've been doing during my PhD, so with David and Jose, which are about studying the diversity that emerges between languages, but also within them. And in particular, what...
Hola, acabamos de llegar a casa. Pues me ha dicho que me ve bien en derecho y que el cierre me lo verá el martes. Y la hora, pues ya me llamarán por teléfono, porque depende del número de operaciones que tengan, pues me darán una hora u otra.
Oh, you mute all and then mute me afterwards. Looks okay. Yeah. Sorry, no worries. So yeah, what the works I will present you are about studying, in particular, how like trying to understand what are the social mechanisms behind the emergence of such diversity that we can see in language. So I'll start with a very general introduction, which first to give you some context about what we're going to talk about and why we are doing so, and then followed by some general methodology that I'll be using in the two works that I'll be presenting afterwards. So to start off, well, what are we talking about? So language is what is known as a cultural universal. So which means that it is present in every known human culture. Like every culture has some form of language. And on top of it, people have been using it, I mean, this kind of system of communication for about tens of thousands of years. So naively, I mean, and that's what we observe as well. We have many individuals, a lot of time has passed, so they have time to come up with all kinds of variations of language. So we have a huge diversity between and within languages. But more recent observations might indicate that you know, if language is just meant for communicating between people, if you want to optimize language for that function, then the optimal state is to have homogeneous language between everyone, so that anyone can communicate with anyone else. But it's a bit more complex than that, because language is a means of communications, but not only, because it's user communication between individuals in different contexts. which play a super important role. For example, in culture, when you are transmitting any cultural traits, mostly you are doing it through language. So many cultural traits are embedded directly within languages, and so much that language is even considered itself part of the cultural heritage of humanity, which is something that the UNESCO said in 2003. And then in the economic sphere, language can be seen as a commodity, because language is a skill and enables you to communicate with different people. For example, if you speak English, you gain some value on the job market. And that's what led, among other things, the sociologist Pierre Bourdieu to say that individuals have different amounts of what he called linguistic capital. And another example is the realm of politics. Because, well, language is so important in everyone's life, but of course, politics is concerned with it. And usually governments have some kind of language ideology that they push for, which can vary between countries, between times. I mean, it changes all the time. It can be from pushing for a uniform language to foment unity between people within a nation. For example, when after the revolution in France, there were lots of pushes for making everyone speak French to make them go to school and everything. Or on the other hand, it can, some policies can push for language preservation. So trying to preserve the diversity that's already there. So from this very general context, what you can gather that, yeah, language is complex. And to study it, in a complex network of interactions, which itself is embedded in a complex social context. The first step that we take every time in the works I will present you is to make some kind of observations. So more particularly, we are going to look more at informal speech, like the most natural kind of speech that we can gather. And we then analyze this language production that we gather, and we do so using computational tools to infer some emerging patterns in the data. Then the second step is to try to understand whatever we have found out, what could be interesting, to uncover the mechanisms that gave rise to these patterns. So what we're doing is theoretical, like physics-like modeling. There's nothing to do with machine learning, where you have models with billions of parameters, like the large language, the recently made famous large language models. Here, what we want is to have models with the fewest possible parameters, and not trying to predict necessarily, but to explain what's going on. So, as I said, the first step is to make some observation, and for that, we need some data. And, well, there are traditional sources in linguistics, mostly, which are mostly published works. So it can go from books, articles, to more recently blogs, for which you have good enough amount of data, because over the years, people have compiled really big corpora. But on the other hand, this is super highly biased, because people who publish things are mostly from the elites, and they write in a very formal genre. Then you have, on the other side, so you try to have a more representative sample. You can do interviews. Then you can eliminate, if you do things right, you can eliminate all the bias, because you have a total control over who you interview. You can know their background and measure whatever you want to measure. But of course, this is extremely costly, because you have to, like, the researcher needs to be involved in the collection directly. And finally, which is, as you can guess, the thing that's going to interest us, is social media, for which we have really large amounts of data, because to register on these platforms, people just have to have internet, basically, and want to do it, because most of them are free. But there's still, of course, some bias, first for the internet access, because worldwide it's not a given. And also, since these social media are made for some kind of audience, there can be different user bases which are not representative of the whole population. And so yeah, that's the compromise that we took in our works. That's to take, in particular, Twitter data. And we're not the first to do so. It has been used in many social linguistic works in the past. Like this review points to lots of them. And here, our data sets are geotag tweets that Antonia gathered from 2015 to 2024. Yeah, so what does the data look like? And what do we do with it? Well, the basic element is just tweets, you can guess. And the first thing that's going to interest us is the text of the tweet, because we want to look at language production. And the first thing we need to do with this text is to extract the meaningful part. So what's actually natural language production. So we clean it out of hashtags, mentions of other users, URLs, whatever, other things as well. And then the second step that we take every time is to pass them through what's known the compact language detector, which enables us to know the language in which the tweet was written. And so yeah, from the text, in the end, what we get is the language of the tweet and any other feature of interest that we may have measured afterwards. The second kind of data that we are interested in is the location of the tweet, because all of them are geotagged. Very few have a very precise longitude and latitude pair attached to them, but most of them have what's called a place as a geotag. Here, for example, it's a city in France, which are represented as a simple bounding box, so a rectangle. And usually what we have is our own sets of cells, that either administrative areas where we have shapes or a square grid that we define ourselves. And when we have this place and we want to actually, sorry? Yes, sure. Yeah, that's, I mean, I made it myself because I was just born, so that's why, indeed. And so, yeah, what we do then with these kind of places, since they can intersect with different, more than one cell, is that we do a partial attribution most of the time. Which relies on like the area of intersection between the place and the cell. So then for a person, we have all their tweets and attributions to different cells. We can also take into account the time at which they have tweeted to infer a set of residents according to some heuristics. So after we've done all that, we have some data, some interesting pattern. Then we turn to modeling, if there's anything interesting, of course. So first, the way we would first start by formulating the model is in an agent-based kind of framework. Because what we want is to have the most flexible setting possible. And so yeah, we just, the model is just formulated in terms of transition probability between states. And then this kind of model enables you to plug in any kind of network of interactions. It can even evolve in time, do whatever you want. But then most of the time, well, always, we also want to get some analytic results, so make some maths. And for that, we have to simplify, obviously. And we do it considering fully connected networks and possibly mean field scenarios. To, for example, obtain, well, simple, more or less, evolution equations and get the fixed points and analyze the stability as well. And in the middle, we have meta population, so which is a population of populations. So we consider that people are in one of the populations, and within them, everyone interacts together, and they can move from one to the other in between steps. And so yeah, you can use this for simulations, but as well for getting some analytic results under some assumptions. So now that I've introduced you, the general context of the work, I can present you the first actual work that I want to present you today, which is about diversity of multilingual societies. So in this one, we are interested in diversity between languages, so different ones. And so the starting premise is that we have interesting systems, multilingual societies, because this language is useful in so many contexts. You would expect, I mean, it's curious that such systems could exist. And like I said before, some linguists, for example, according to observation, but also some trends in the communication network, etc., I've been worried about homogenization of language, and in particular what they call the max extinction of languages, which is kind of already happening. And also a bit more recently, but like 20 years ago, some physicists have also tried to contribute ideas to this issue, mostly doing modeling of language competition. And a prime example of that is the model by Abrams and Strogatz in 2003. It's a super simple evolution equation, like differential evolution equation, but they just fit to historical data. Here it's the evolution of the proportion of Scottish Gaelic speakers. And they just fitted the model and claimed that these languages are going to die according to their modeling. Now, what we want to do is to start by, because these are concerned with just a few examples, we wanted to first explore the variety of multilingual societies, and especially the spatial patterns, how people coexist in space or not. And we do so, well, not very. So we do so looking at geotaxons, like I mentioned already, to infer spatial distributions of language use in multilingual societies. So yeah, from the data we have gathered on our analysis, the basic thing we get is this number, NLI, which is just the number of individuals of each language group in each square cell I. Because we just laid a square grid over each region of interest, and we just mapped to this grid. And here language groups can be monolinguals, bilinguals, trilinguals, whatever. And what we want to see in space is how much people mix together, or conversely, how much segregated they are. And we define, in this case, our language segregation as a departure from a normal model in which we would have language groups distributed exactly like the whole population is in space. So to illustrate that, we can define a proportion entropy in each cell, which is just the entropy of the proportions of each language group in that cell. We make the ratio, we compute the ratio with its value, its no model, and we get a relative entropy that allows us to quantify the mixing in the cell I. And here I show you two paradigmatic examples, which are Belgium on the left and Catalonia on the right. Here the color bar shows you in white at the value 1, like cells where you have the most mixing, there is no segregation in them, regarding language groups, of course. And any value at the extremes in blue or red indicates segregation. And the difference is extremely clear. In Belgium, we have no mixing at all, except on the border between Flanders in the north and Wallonia in the south. And also except in Brussels and some part of the east of the country. Whereas in Catalonia, you have a much more mixed and uniform picture. So having observed this kind of completely different states and also others that are in the paper, we proposed an agent-based model. I mean, we formulated one, in which we have two main processes at play. So first, in the transitions up there, you have a bilingual dying, which can result in a transition to a monolingual state because they lose the language when they are replaced by their offspring. Here, the population is fixed, so if someone dies, they're replaced by a new person, and that's it. Then the other kind of process at play is that the monolingual could learn a language, the other one. And we have this parameter C, so yeah, the mu was the mortality rate, and in the bottom we have this parameter C modulating for the learning rate. Then we have the prestige at we denote S, which is just how much the language is preferred in distributions and the whole, like outside of, like in a very overt way. And so this is the one for language A. Then this prestige will modulate the social pressure term, let's say, which is based on the proportions of the language group that are around the agent that we consider. And so for monolinguals, for example, the more A monolinguals you have, the more when the bilingual AB dies, the more probable it is that it will become a monolingual in A. But then for the bilingual, the proportion of bilinguals, it plays a different role because we choose some kind of bias that they can have. So it's a preference to speak the language A. And in this case, it modulates this transition. So to make it more probable in this case that they switch to A. Mm-hmm.
What is the mortality rate here? Is real speculation? Is there one mortality?
I mean, in all the following, it will just be said that you have a probability of 2% to die at a rate. No.
When one individual disappears, then another one replaces.
Yeah. Yes.
This population,
yeah, the passing of generations and yeah. Well, this is the probability not to die. Stay alive in that time step. I mean, it's not really a rate. It's more like a probability to die in each time step, if you want. It could be, or they could retain, like you have 1 minus this probability, that they retain 1 minus this one to stay in because here the process is that but they die in this case only they can use the language. And here there is this C that's kind of the learning rate that says while they are living, they have some probability to learn the other language. Like C is the maximum probability to learn the other language at the time step.
Assume that when the parent is bilingual, then the child is so this model assumes that when the parent is bilingual, then the child inherits one of the two languages and not the two.
Now they can keep the two, but
well, but in this figure here, okay, and then 1 minus mu is that if you stay alive, you can learn another language, and then you become bilingual.
So, as I said before, now that we have defined this model, we'll just set it in the simplest setting possible. So we consider a single population, fully connected, and study the model in field. And here I show you 3 kinds of stable fixed points on the model. So on the x-axis, you have the proportion of P of monolinguals in A, and on the y-axis, the monolinguals in B. And here on the left, for a neutral prestige and preference, so people don't care about there's no bias in any way. When you have a low learning rate, The only possible stable fixed points are the ones where you have only one language surviving. When you increase this learning rate, you get the other fixed points that becomes the stable one, which corresponds to every language group, surviving. And more interestingly, when you have a bias of the prestige toward the language A, but the bilinguals prefer language B, and you have a quite high learning rate, you have this kind of state in which you have both bilinguals in A and bilinguals in AB. So B is actually surviving only through the population of bilinguals, which is in a minority. Okay, but then what really interested us in the beginning was to study spatial patterns and try to explain them with the model. And we did so using meta-population simulations. So here, each population is just a population in a cell. And we use data from the census regarding commuting to assign our population of agents, residents, and a work cell. And so the simulation two kind of steps. One in which people stay in their home cell and interact with who is there. Then they move to work in the second step and interact with whoever they find them. And we just iterate the model until we reach some kind of stable state. And what's just interesting to see is that on top of the two kind of states of extinction dominance all mixing that we have in a single population, you have a third one in these meta-population simulations, which is one where you have the two languages surviving, but in completely separate communities, with a stable boundary between the two communities, which is the example that I show here. So I initialize the data as I had it on with the Twitter data. I run it and I get this stable boundary. And when you increase a lot the learning rate, you get complete spatial mixing. The border blows up, and most people get bilinguals. And so, yeah, one final result I want to show you about this model is this simulation in which we show the importance of the initial conditions on the dynamics. So here we start with super low values of the learning rate, C, and I will increase it with time. First we reach the stable state and then we increase it. Sorry, I didn't say what the colors meant. Here the color bar is about the polarization towards French. So when you have high values in blue, close to 1, means everyone speaks French. When it's at 0, everyone speaks Flemish, and in the middle, the two are balanced. Mostly through that, and it was mostly. And so, yeah, when you have reached high values of C, you just get this completely uniform picture with lots of bilinguals. And when you decrease it again, we wanted to see like what if a border would appear again and where. And yeah, you get a random placement of the border, which changes from simulation to simulation, of course, which shows that the current state is well dependent on the initial conditions that led to it. So to wrap up this first project, we used geotag tweets in which we detected the language and extracted the distributions of languages spoken in more than 15 regions of interest. Then we measured the language mixing and quantified this thing to observe that we have a rich variety of multilingual societies. And finally, we developed a model which includes both this relative ease to learn the level language and preference of bilinguals for one of the two languages. And we obtained that the coexistence is possible, and including some special interactions involving setting the model in space, we find that we can have a stable boundary between two communities. And you can find the paper at this reference if you wish. Okay, so that's it for this work. Now I will switch to another one. As you can see, the structure will be more or less the same because it relies on the same methodological basis. And this one we're interested in socioeconomic status. and variation within a language. In particular, here we look at English in England and Wales. And so yeah, the issue we are concerned with is the interdependence between socioeconomic status and language variation. You have some empirical results regarding this that have been published in the past. For example, every report of the OECD, the PISA report, every PISA report of the OECD shows even in developed countries, when you look at the reading proficiency of 15-year-olds, the ones with lower socioeconomic background consistently perform worse. Then you have also this seminar work by a linguist called Laboff, where he went to stores in New York City, interviewed people in them, and well, the stores that he visited were not by chance. He selected ones based on what kind of the kind of people they market to. So people for store for rich people, for poor people, etc. And he found that there was a strong correlation between the accent variation of people and their socioeconomic status, using this proxy of the store they visited. And more recently, and more closer to what we do, there is this work by Abitbol, and one of the co-authors already mentioned is Martin Kapsai, who's one of the contributors of this work. So yeah, using Twitter data in France, they have shown that non-standard language correlates with socioeconomic status, but not only. Also, if you look at geography, for example, in France, in the north, people speak less standard than in the south, when you look at the global picture. So, so yeah, we wanted to use also our data set of attack tweets to look into this issue. And yeah, the first question was, how can we actually measure the deviation from standard languages based on the tweets that people post? So first, as in the previous work, we identify the residents by areas, which are in this case 7,000 administrative areas of England and Wales, which have a typical population of 10,000. And on each of these tweets, I mean, each of the tweets of these identified residents, we run a tool called Language Tool, which is a grammar and spell checker. So here to give you an example on this quote by former French President François Hollande, you get, I mean, the tool gives you where there's a mistake and what kind of mistake was done, and how to correct it, but this is not relevant to us. So we just run this thing on every tweet we had for these users. And then we get mistake frequencies of these 100,030 users that we had, which are residents of one of 4,900 areas that are left. Because of course, in some areas we didn't identify enough users, so we did this problem. Then what we are interested in actually is to use this frequency of grammar, in particular of grammar mistakes, and see if it's correlated somehow with socioeconomic status. To get access to socioeconomic status, we use the data from the census, giving us the average net income of people in that area. And then we'll just measure correlations. You can see here where each point is a cell. And you can see for England and Wales, there is a rather low correlation. Like the correlation is quite weak, minus 0.25, but it's significant when you look at the p-value. However, when you zoom in on a particular city or metropolitan area, this correlation varies a lot between, for example, Manchester and Sheffield. In Manchester, you have much more correlation. In Sheffield, there's absolutely no correlation. The p-value is super high, and even the value of the R value is really close to 0. So then we wondered what could be the reason that made these cities so different in that regard. And so we looked at associativity, which in this case means, which is the one defined in this paper and other ones. In this case, it just means the tendency that people have to mix with others who have the same kind of socioeconomic background. And we do it using mobility between cells that we measured again with our geotag tweets. So we define 5 classes, which are defined based on, such that you get people population in each class, and measure the assortativity by city. And then we plot it here on the x-axis. On the y-axis are the correlations that I've shown you before, but for more cities. And as you can see, the more classes mix, so the lower the assortativity, like here in Sheffield, the less conforming to standard rules will actually be correlated with the socioeconomic status of the person, of, well, the area. So again, we have some kind of interesting pattern, and we wanted to model it, to try to contribute some understanding to this issue. So the model just considers 2 varieties, 1 and 2, which would be non-standard and standard. And in this case, 2 classes, so the poor and the richer people. And first you have, so these are the transition probabilities based on each class. So the class 2 are circles, the class 1 are triangles. And a field form means that you have the person speaking standard and an empty one that's speaking non-standard. And so the first parameter is again the prestige. Well, this time we noted LV for some reason, which is the one of variety 2. So the prestige of the standard one, which will usually be above 0.5. Then you have 2 Qs, which are again preferences. Q1 is the preference of class 1 for variety 1, and the same for Q2 for variety 2. The Q2 will fix it, because we will consider that richer people are neutral about, like they don't have any cultural preference or whatever for any variety. And the last ingredient is the mobility between cells. So we introduce this matrix of MIJs, which gives you the probabilities for residents of each cell I to move to another cell J. And so, for instance, so people move from cell to cell and they interact with another one at random. And for example, when you are a person of class 1 interacting with a standard form, so with another person picking standard, you have a probability LV times 1 minus Q1 to switch to this state, speaking standard. So you have this Q1 which goes against the prestige.
The shape denotes the variety or the
social class. And filling or not filled denotes the variety. Okay, so then we set this model in field to try to get some insight about its behavior. And we consider that the classes 1 and 2 are each in their own cell, are completely separated. They have the same population and the same outward mobility. So the outward mobility is just the probability to go from your cell to the other one. And we get this kind of evolution equation, for example, here for P1, which is the proportion of people of class 1 that use the variety 1. And there are there's a competition between 2 kinds of terms. One which is related to the mobility, which is maximum for n equals 0.5, because that's the value for which people mix the most. And this term pushes P1s towards 1 minus P2. So actually towards a more homogeneous language, like towards no difference of variety usage between the 2 classes, because this term is always positive. And then you have a second term, which you can label as one of cell growth, which will push P1 either towards 0 or 1, depending on the sign of this term, which is the difference between the preference of these people for their own variety and the prestige. And you have the same kind of equation for P2 with exactly the same kind of effects. Then we looked at the fixed points of the system of equations we had. So here in the 3 panels, the first 3 ones, we fixed Q1 at 0.7. People of class 1, sorry, highly prefer variety 1 and some kind of average mobility at 0.2. And when we vary the value of the prestige, you can see that when it's rather low, then the stable state is when only variety 1 stays alive. At some intermediary value, the two of them stay alive. And when it reaches Q1, the only stable state is the one where only the variety 2, so the standard language, survives. And so, yeah, as we saw before, whether you get extinction, dominance, or coexistence depends on the sign of Q1 minus LD when you fix this parameter. And the last panel shows you, so it's a parametric plot showing you for fixed values of Q1 each time. When you increase the value of n on the color bar, where does the stable fixed point, this corresponding to this one, the one of coexistence, where does it move in this space, in this P1, P2 space? And as we saw before, just with away the arguments, indeed you get closer to the P2 equals y minus P1 line. And then in which direction you go depends on the value of Q1. And yeah, sorry, this is a first thing that's consistent with the observations. The more people mix together, so the more you increase n, the more they are going to speak more or less the same. Then we wanted to look at the parameter space and the kind of stable, when the kind of stable solutions are enabled. So here again, Q2 is just fixed at 0.5. And on the left, you have the prestige fixed at 0.6. And you have the free states that we just talked about. So only variety 2 surviving, only variety 1 surviving for really high values of Q1 and high mobility. And the state where you have the two varieties surviving. And so you can see that in general, when you increase mixing between the two, this tends to limit coexistence. But for a small range of values of Q1, which is more than, like, where you have a good equilibrium between the two varieties, whatever the mixing you get into this population, between these populations, you will still get coexistence. And here, for example, if you follow a vertical line, like this one as 0.65, more or less here, you can see here that when you increase the value of n, you will reach actually extinction before you get to 0.5. Okay, so now I will turn to some first simulation results we have. So this is kind of preliminary. So to run these simulations, we use the population we had from the census in all areas of interest, the 4,100. No, actually the 7,000 ones, because in this case we want to simulate with the whole thing, and then we measure everything on the subset that we had in the data to compare between the two. And again, to conform to the observation that we made, here we define 5 classes again in the model. So it's very simple. You just need to introduce 3 more values of Qs. But to limit the number of simulations we do, we just do here simplification. That the bias toward variety 1 of each class will just be like a linear interpolation between Q1, which is the preference of class 1, and 1 minus Q2, Q2 being the preference of the richest class, so class 5 in this case. And so, yeah, for example, for these values, so standard language being slightly preferred overall, and a rather high preference of class 1 for the variety 1. We get our cities. So here on the thing we measure is the value on the y-axis. So yeah, at the end of the simulation, we just measure the proportion in each cell of the variety 1. And when we plot it against assortativity, like we did in the data with the frequency of grammar mistakes, we get more or less the same kind of relative positions of we want to get more results out of it. I know it's very preliminary, but yeah, that's what we have. So to wrap up this second project, this time from geotype tweets, we use a grammar checker to actually map the average frequency of grammar mistakes in the whales, as seen on Twitter. We then measured the correlation between this frequency of mistakes and the proxy that we have for socioeconomic status. And we found a slight tendency for our socioeconomic status to deviate from the standard form, but it's not uniform across different cities. And then we compute the assortativity in mobility, and we've shown that the more social mixing you have, the less interdependence there is between socioeconomic status and non-standard usage. And finally, we pose an Asian-based model of variety adoption. We have an overt, like external prestige, and a covert one within each group. And we have shown that it captures well this effect, both analytically and in simulations. All right, that's it for me. You can find all source materials, the code on GitHub, the data on my Open Science Framework profile. So aggregating data, of course. Yeah, you can reach me or ask me questions now. Thanks.
Thank you, Thomas. So, well, there were already a few questions. Maybe you have comments or even further questions. Gonzalo? Thank you.
Well, that's the difference between the data and the simulation. So in the data, we just measure the frequency, like the average frequency of our users of making grammar mistakes. So every X word, they make a grammar mistake, for example, on average. And in the simulations, where we don't measure that, we just say they use variety 1 or they use variety 2. They speak standard or not.
Great. Thank you.
More questions?
Thank you, Thomas. I got lost at some point when you talked about the prestige and how the fixed point change depending on the prestige.
In which model?
And the second one.
Okay. So these plots?
These plots.
So we want me to explain again, I guess.
Yeah.
Okay.
Thanks.
So,
Very good.
so here on this plot, you have on the x-axis P1, so the proportion of people of class 1 who speak variety 1, so standard, non-standard, sorry. On the y-axis, P2, the proportion of people in class 2 who speak variety 2. In these three plots, we have fixed values of the mobility and of Q1, which is at 0.7. This is the important thing. So variety 1 will, class 1 will actually prefer to use their variety, their corresponding variety. And here we just have 3 example values of the prestige.
But you define as?
Just with arbitrary values to illustrate. It's
no, the interpretation. What is the prestige of the variety?
It would be that, for example, in education, people are taught that this is the correct way to speak or to write in this case.
Okay.
But in the media, they use this kind of language, etc. It's all the external influences that tell you this is the correct way.
Okay, okay.
And then there's between your group, you actually want to put something different, and you can have the preference for your own variety.
Okay.
Hi. I don't understand how do you distinguish, so how do you define the standard and non-standard way of writing from the data? I mean, probably there are many non-standard ways to write. For example, there can be geographical differences. People closer to Scotland or closer to Wales, perhaps this is not correlated to with socio-economical status, but it's also changing the way they write. Is this any way to distinguish that or to implement this in the model, or is not necessary?
Yeah, I mean, in this case, we just considered either you speak standard or non-standard, and we put everything that's away from the standard as non-standard. There can be many different dimensions of non-standard, let's say. But that's kind of the reason why we focused on grammar mistakes, because this tool can actually give you other kinds of mistakes, such as this word doesn't exist. Many different things I can't think of now. But yeah, in this case, we focus on grammar because it's maybe the most neutral and the thing that you learn in school and that shouldn't be moved. And well, it happens that people play with it, but like when you have a dialect that mostly introduces lexical items, for example, it will be okay. But of course, there are effects on grammar as well. Yeah, each one which is considered a grammar one is considered equal.
Because perhaps you can also think about what is the information that the sentence conveys, or are also measures about this kind of.
In terms of the complexity of the ideas that people.
Yeah, how random the sentence is, no, with respect.
No, but nobody understood what he meant. No, it's not a tweet, but it's a quote. He said it in, I don't know if it was an interview.
I have a question about the first model. When you saw the stability of the fixed point, I suppose that there you are using a main field model, no? Something like that. How is the transition from one of the situations to the other? I mean, you lost the stability of the middle fixed point, and at the other way around, no? You have the stability on the left, and then you have only stability of the bilingual thing. How this transition occurs?
I don't know. If I remember the phase diagram. Oh. You remember what the phase diagram looks like? Because I mean, we do the same thing as the other work, but in this case, I don't remember exactly how it looks. But most of the time, you do some element of response. Otherwise, it's in the thing. Most of the time, when you increase the relative ease to the other language, you will tend to increase the number of bilinguals. And so it will push towards 0, because here it just you just consider a proportion of monolinguals. And yeah, this point will become more. I mean, there's a sharp transition between this one being non-stable and then stable. And we have a phase diagram shows one.
Do you have any intermediate state where you have also a stability of the mixed, well, let's call it and also the mono speakers, the bilinguals and the, I don't know how to explain it, but I think
yeah, I mean, this point in blue and this one as well.
Yeah, for example, or some other solutions in the middle or something like that.
From what I remember, no. So
that would be the case of Benjamin, and that would be the case of Catalan.
Yeah, but you're changing just one parameter, no? I mean,
yes, just the similarity between the
dimensions. So the change should be smooth. I assume that there is a, well, from a bifurcation theory point of view, I assume that there is going to be some kind of pitchfork and then some transcritical to change the stability of the middle point and one of the streams. So probably you have other kind of scenarios in the middle. I mean, for me, the transition to one to another should be continuous.
I don't remember. No.
Okay.
So you showed this data for associativity in different English cities, and I noticed that Manchester and Sheffield were very different from each other. Do you know why? What causes that? Or what's the origin of that?
To be honest, I don't know.
Yeah, there was another plot where you had the explicitly the associativity for different cities, no? And
I don't, because I remember looking at some maps. I don't know if it was in Sheffield, but the university was super close to the city center. There was one city like this one, I mean, with such a case. So we had lots of poor students living super close to the rich center. And I know what you meant just regarding.
no, I think it was the next. I think it was the next one of the next slides. That one, yeah.
Yeah. No, I mean, to be honest, no.
But we do have the
Yeah, like that.
But I mean, he's also in this. I think we could see that in the case of Sheffield, people needs are not people.
Yeah. But I'm just wondering why. Why that is? Why?
As he said, sometimes the campus of the campus is closer to the poor area or to the rich area. So, any questions? Okay, so let's thank Thomas again.